start. So welcome everyone to this colloquium this morning instead of the usual afternoon slot. It's my great pleasure to introduce our speaker for today, Professor Chen. Shia received her PhD from MIT, working at the interface of quantum information and condensed matter physics. She spent a few years as a Miller Fellow at Berkeley before taking up her current position as a professor at Caltech, where she's been for several years now. So Shia works at kind of this interface of quantum information and condensed matter, where she's made a huge number of contributions. She has received many honors and awards for her work, including the Sloan Fellowship and the New Horizons Prize a couple of years ago, which is given out to basically to the superstars of physics. It's like the Oscar awards for physicists, and so it's very nice that to have her give a colloquium. She is currently in China, so we had to kind of reschedule our time slot, but I can see that there's a fair number of people who made it to the talk. So without further ado, let me hand over to Shia for her talk.
Thank you, Arun, and thank you everyone for coming. Yes, as Arun mentioned, I'm currently in China, so sorry I cannot come in person, and I have to move the time slot to early in the morning. So for those of you who are here, thanks for coming. For those of you who cannot make it, I was told that the talk is recorded. So so hopefully I can share with you, even through Zoom, this exciting topic of how quantum matter correction codes can turn out to be exotic condensed matter. So this is the area I've been excited about and working on over the past years. And especially, I want to tell you about this new topic called fractal. It's a new research area involving both quantum information and condensed matter, and also field theory, as I would mention in later part of the talk. And I want to tell you the story of how people try to make quantum error correction codes, but turns out to inspire studies in condensed matter and field theory. Okay. All right. So let me see. Okay, so first let me clarify that when I say code, I don't mean the kind of code we're writing, Mathematica or MATLAB, but instead this is error correction code, meaning that if we have some information and we try to encode it in a safer, more reliable way for doing computation or communication, so we turn those simple classical bits in a more complicated way, so the information will be protected. So let me first give you some very, very naive introduction to the idea of error correction code, of course, starting from the classical one, the classical error correction code. And the simplest error correction code in the classical world is designed to correct for what we call the bit flip error. In a classical computer or a communication channel, we have zeros and ones representing information, and errors happen by flipping a 0 to a 1 or 1 to a 0. And the most naive way to protect that information against this bit flip error is to use something called the repetition code, meaning that if I want to transmit a message, I can say that 3 times. I can encode a 0 into 000, or a 1 into 111. And then instead of sending just 1 bit, I can send 3 bits down the communication channel. And let's say the bit flip error happened with some small probability. Then for most of the messages, they still stay as 000, but with small probability, it turns into 001. And with even smaller probability, it turns into 011. And in the worst case, with smallest probability, it becomes 111. Okay, and the reverse thing happens for the 111 message, where it mostly stays at 111, but with some small probability, some of the bits get flipped. Okay. So after the information has passed the communication channel, it gets all kinds of error. But when we receive the message, we'll check for how many bits are, we'll check for the zeros and ones, and we'll decide on a decoding scheme. And in this case, for example, we can decide that if we see the majority of the bits to be 0, we'll decode it to be back to 0. And if we see the majority of the bits to be 1, we'll decode it to be back to 1. So error does happen through the channel, but it happens with a smaller probability when we encode 1 bit into 3 bits of repetition code. And this is the idea of basically classical error correction. And with this particular error correction scheme, we can correct 1 bit flip error, because if only 1 bit gets flipped, we can still correctly recover the message. So we say that the code has distance 1. Okay. And very naturally, we can generalize the idea to the quantum world. And this is a big development back in the 90s, that people realized that we can do error correction for quantum information as well. So quantumly, we don't just have zeros and ones, but we have any superposition of alpha 0 plus beta 1. So there was actually a big debate about whether error correction can still work, but amazingly, it does. And what people realize is that besides bit flip error, which flips 0 to 1 and 1 to 0, there's in addition a phase flip error, which turns 0 plus 1 into 0 minus 1. And this is something that didn't happen in the classical world. It only happens quantum mechanically, because now there's superposition, and we can change the superposition. So we can try to come up with ways to design error correction code for the quantum information. For example, we can encode the state of 0 into 0, 0, 0, and 1 into 1, 1, 1. So doing something like a repetition code for quantum information. But we'll see that this is not the best way to do it, because now if we make a superposition between the logical 0 and 1, we get 0, 0, 0 plus 1, 1, 1. And this is, as I said, this kind of encoding is good for the bit flip error, because it can safely recover if only 1 bit flip error happens. But it's not good enough for the phase flip error, because once we make this superposition, it could happen that 1 phase flip error happens on 1 of the qubit. And then suddenly the whole superposition turns into 0, 0, 0 minus 1, 1, 1. And then if we decode, we'll get back to 0 minus 1. So the message completely changes. The state we end up with is orthogonal to the state we start with. So this means that for phase flip error, this kind of encoding is bad, and that we cannot even tolerate one error happening. But people are smart, and so back in the idea is that we need to design quantum error correction code so that locally on each qubit, it needs to look indistinguishable. That there shouldn't be any information embodied if you look locally at the code. And that turns out to be the essential idea underlying the design of quantum error correction code, because otherwise you can just apply a quantum operation and change the message that's encoded. Okay. So Peter Shor was one of the people that came up with nice ideas of designing quantum error correction code. And the idea is actually pretty simple. He said that, well, if the simple repetition encoding doesn't work, then let's take the superposition of 0, 0, 0 plus 1, 1, 1 and do 3 copies of that. So do a repetition of that superposition, and then it works. So it turns out that this is a 9-qubit code. With 9 qubits, we can safely encode a single qubit of information, and then this 9-qubit code would be locally indistinguishable. If you look at any of the 9 qubit, you will see that the encoding of 0 and encoding of 1 look completely the same at the level of single qubit. But of course, if you look all 9 qubits together, they look different. And the nice thing about this 9 qubit encoding is that it can safely correct 1 bit flip error and as well as 1 phase flip error. So this is a quantum error correction code with distance 1 for any type of quantum error. Sorry. Oops. Okay, so that's a very brief introduction to quantum error correction code. And as my title suggested, I'm trying to bring together 2 very different subjects, and the second one is called condensed matter. Well, condensed matter has a totally independent history, and it started from the study of things as I show on this page. It's crystals, magnets, sticky fluids, metals. Of course, then in the 20th century, then people realized that these matters can have quantum mechanical behavior as well. For example, if we cool them down to low temperature or put them in the right environment, we can have superconductor, superfluid, or even things like graphene. But how can this be related to the kind of quantum error correction codes I was talking about? Because error correction codes sounds like some mathematical idea that you write down on paper, totally contrived and pretty small, right? You start from 1 bit and 3 bit and 9 bit and not very big. On the other hand, quantum condensed matter involves 10 to the 23rd number of atoms. It is quantum, it's true, but it's more natural. People, at least the field started, where people took real physical materials and then studied their physical properties. So the starting point of these 2 fields are completely different. So how are they related to each other? Well, so for error correction code, actually, it can't be completely contrived, because if you want to actually realize it, you have to put it into a physical system. For example, you encode the qubit into photons or into superconducting qubits or into trapped ions, and then it becomes physical. And moreover, if we try to have a good code, then we want the code to have very big distance, to have even macroscopic distance. So we need a huge code, a big code, in order to encode our information. And one of the a nice prototypical example of such macroscopic distance is the kind of hard drive that we have. And this is actually an example that I'll come back to when I talk about Fractal. And the quantum version of the hard drive is something that inspired the whole area of Fractal. But here I'm just showing a classical hard drive. Everybody of us have a hard drive, and we know that the most naive way to understand how hard drive works is that it's a magnetic disk, and there are magnetic domains where the magnets can point, the domains can point up or down, and the up or down encode the 0 and 1. And of course, there are a lot of little magnets inside each domain. So this is a macroscopic encoding with macroscopic distance, basically a repetition code. And then once we come to the quantum world, we need more and more quantum mechanical degrees of freedom in order to have big quantum code. And then people start to put superconducting circuits together into a 2-dimensional array, or code atoms together into an array. And then within such quantum mechanical systems, we can try to design and realize and manipulate quantum error correction codes. But this is also how quantum condensed matter could look like nowadays. And you see a lot of papers which talk about quantum simulation of quantum matter within superconducting circuits. and within code atoms in two-dimensional optical lattice, for example. And here are just some of the articles that I pull out from the literature about quantum simulation with ultra-cold quantum gases or superconducting circuits or with trapped ions. And you see that quantum correction codes and quantum condensed matter start to look more close to each other. And indeed, these two come together. They really become two fields of the same thing when we consider them as locally addressable quantum many-body system. Okay, so first of all, it has to be quantum. Secondly, it's a many-body system because we want a big system, so there can be a code with a large distance and also a condensed matter system with lots of degrees of freedom. But also we want it to be locally addressable. And for the quantum error correction, this is because we need to encode information, we need to detect the errors happening, and then we need to decode the information. So we need to locally act on this quantum system. And for quantum condensed matter, this is just the new era of designing material where we're not just taking whatever nature is giving us, but rather we're putting quantum degrees of freedom together and try to design their interaction with this local addressability so that we can actually achieve things that's not naturally, that may not be very natural in the kind of material that we find. And this would lead to, for the quantum error correction codes, better codes, and also lead to realization of them in physically more natural and physical system. And on the other hand, for the quantum condensed matter, this gives us, this leads to quantum information application of such systems and reviews novel features of quantum matter. And for the rest of the talk, I plan to tell you two such examples where quantum error correction codes turns out to be very nice examples of exotic condensed matter. And these two, one of them is so-called the topological systems, and the other is called fractonic. So topological systems has been around, people have been studying them for decades, while the fractonic one is more recent. It's something that many groups are involving, and my group has also did quite some work on this topic. So I'll try to start from the topological one, which people might heard more about, and to give you a flavor of how things went, and then tell you about this whole new topic of fractal code and fractal matter, and tell you what, well, tell a little bit about what the whole field is trying to understand, and especially about what we have been doing on this topic. Right, so this is just to illustrate the idea of how the study of quantum error correction codes can become exciting topics in quantum condensed matter. So the first one is topological matter / code. So as the name suggests, topology plays a very important role in either the matter side or the code side. So here, topology, by topology, I'm referring to the kind of feature in a shape where it doesn't change under continuous deformation. For example, if you have these kind of 2D surfaces, you can ask how many holes are there. And the first one is a sphere, it doesn't have holes. The second one is a torus, it has one hole, and the third one has 2 holes. So the 3 blue shapes have different topology as 2-dimensional surfaces. So small deformation, small continuous deformation wouldn't change the number of holes, but of course, if you do a large deformation, you might squeeze the hole, but that's not allowed. Okay, so under that kind of assumption, we would say that the torus is equivalent to this coffee mug, because they both have just one hole. So this is the mathematical idea of topology. So how is it related to quantum error correction code? Well, remember that one of the key idea that goes into designing a good error correction code is that that the code has to be locally indistinguishable. That locally, if you look at the code, you can't tell whether it's a 0 or a 1. Okay. And that idea led to the design of what's called toric code. And toric code is a code that's designed on a two-dimensional surface, and in particular on this two-dimensional torus. Okay, so it turns out the quantum degrees of freedom on this two-dimensional torus is designed to, first of all, form a grid. And then each of the degrees of freedom can be either in the black state or the red state. And then the code says that the red state has to connect into loops. So I've drawing some kind of configuration that you see. The first one has no red loops, and the second one has 1, the third one has 1, and then you can have multiple loops, and you can have loops of different shape and of different location. And eventually we make a superposition of all kinds of such loop configuration. And that gives one of the code word that gives us, for example, the logical 0. Okay. And then what's the logical 1? Well, remember that there are these non-trivial cycles on the torus, and we can try to add that into the two-dimensional grid that we have for the physical qubits. So when I'm drawing the two-dimensional grid, I assume the periodic boundary condition. So here and here is a periodic boundary condition, and also here and here is a periodic boundary condition. So by adding a non-trivial loop onto the torus, what I'm doing is that I'm drawing red lines like this, and it merges into the original configuration and changes them individually. But what's nice about this kind of encoding is that because originally the whole state is a superposition of all kinds of fluctuating loops. So after adding this non-trivial loop, but if you stay locally on the torus, if you're just a microscopic a bug looking locally on the torus, you wouldn't even know that there is a non-trivial loop on the torus. You would only notice that if you traverse the whole system, and then you can observe that there has been a non-trivial loop added. But otherwise, you just see the loops moving around you and fluctuating in all possible way. So locally, there's no way to tell the difference between this state and the previous state, and that's exactly what we needed in order to do quantum error correction. So of course, for the torus, you can also add it in the other way because there's another non-trivial loop. So it turns out that for toric code, we can actually have 4 logical states. The first one was no non-trivial loop, the second one was 1, the third one was the other one, and the fourth one was both. Okay. So this quantum error correction code can be used to encode 2 qubits or a 4-dimensional Hilbert space. And it has a very big distance because as long as you look at a finite patch of the torus, you wouldn't be able to tell whether there are big loops or not. So it's a code of distance that scales as the linear size of the system, and that's why it's a good code, right? It's something that we talk about we want because it's a code with macroscopic distance. As long as you make the code bigger, the distance grows bigger. Okay. And this is, of course, a very contrived model specifying how the qubits needs to be organized and that they connect to loops and then they fluctuate. But what's amazing is that this kind of physics is not completely imaginary. It does exist in real physical systems, and in particular, people have made proposals, although experimentally there's still controversy, but there have been various proposals of how this kind of error correction capability is embodied in real physical system, either in made up quantum mechanical system like cold atoms in optical lattice, or in more and more realistic quantum materials like graphene, or even this bluish crystal called Herber-Schmittite. Okay, so of course in Herber-Schmittite we cannot imagine that the degrees of freedom would try to connect into loops. That's not what they do, but instead it actually can be the result of highly physical, highly realistic type of interaction. For example, spins, neighboring spins having antiferromagnetic interaction, like just the S.S spin interaction. So this is the theoretical proposal, of course, that on this kind of lattice or some other kinds of lattice with the kind of antiferromagnetic Heisenberg interaction, it is possible that the ground space would actually be having the same kind of error correction capability as the toy model that I showed on the previous page. So this is the point where error correction code jumps into condensed matter, and people are trying very hard to realize these kind of systems in either optical lattice or in these kind of real materials, to actually have a system that will allow us to encode information and to encode it in a reliable way. And the reason people want to do that is because Tori code, along with many other codes, have been proposed to be the very important starting point for fault-tolerant quantum computation. Because quantum computation is hard because it suffers from all kinds of decoherence, all kinds of errors. But if we can encode information in a reliable way, that might give us an opening to perform quantum computation for as long as we want. Okay, so one of the idea, for example, is to take toric code or take any physical system that realizes the same error correction capacity as the toric code and have it on a two-dimensional sheet. And then, of course, this will give us the capability to encode a few qubits, but if we want to do computation, we need to do something more. And the extra ingredient people propose here is to just punch some holes in the two-dimensional surface. So here's a one hole, here's a one hole, here's one hole. And the way information can then be manipulated, be operated upon, is to draw lines around these holes. And so, for example, you can draw a figure 8, or you can draw multiple circles around some of these holes. And because information is encoded topologically, so as long as there's a hole in the surface, then it makes a difference. For example, whether the red line is going around the hole one time or two times, and that will give us a way to implement quantum operation in a topologically stable way. So that's basically the idea of topological quantum computation, which is very nicely illustrated by this figure on Scientific America, where you have a two-dimensional system. And then, well, on this picture, instead of punching holes, you're just making some ripples, generating some kinds of defect in the system. And then the way the information can be encoded inside these defects, and then operations can be applied on these encoded information by dragging these defects around each other, so that eventually computation will depend on the topological features of the trajectory of how these defects move around. For example, how many cycles, instead of what's the exact trajectory of them moving around each other. And of course, the goal is to actually do that within either real material or made up quantum mechanical systems like the optical lattice. And people are making a lot of progress actually along that line in recent decades. But that's not the main topic of my talk today. And what I want to tell you for my talk today is the so-called fractal matter and fractal code. And this is what we have been most excited about in the last couple of years, because for the topological one, the connection from toric code to these topological material is nice, but it's not that surprising because topological order was kind of already known way before the discovery of toric code. Toric code provides a very nice example, a very nice toy model to understand what is going on. It led to a huge development in the area, but without toric code, people do know the existence of topological order. But for Fractal, it actually was a total surprise that the discovery of error correction code, the kind of error correction code, told people that we are just ignoring something that exists physically, but it never occurred to physicists that this kind of feature can exist in a many-body quantum system. Okay, and that has to do, the story has to do with hard drive, as I said before, that I would come back to this. So let me come back to talk more about classical hard drive. Okay. So classical hard drive is basically a 2D magnet.
Shia, yes. Somehow your screen is frozen. I don't know if you want to.
Oh, is it my slides or is it my video?
No, sorry, not the video, the slide. Yeah, it's on the Fractal Matter code. It's not switched if you want to. Yeah, that's
so,
yeah. Mm-hmm.
Oh, okay, so maybe it's just slow. Yeah, sorry. Okay, so I'm on the page about classical hard drive, and I'm trying to explain that this is just a 2D magnet, and there can be magnetic domains encoding zeros and ones. Okay, and sorry, yeah, right. So what the hard drive does is to store classical bits of 0 and 1. And we want to do it with finite error rate. And we don't want to, and the key is that we don't want to actively correct for error, because once we write the information into the hard drive, we want to unplug it and put the hard drive in a drawer and then come back a week or a month or a year later to safely retrieve the information. So in that sense, we want the error correction to be passive. We want the protection to be passive. And eventually, of course, we want this to work for a long time. Well, you can define what's a long time, but the hard drive we have today is very reliable, right? It can work for years or decades. So in the classical world, hard drive is actually, well, not a very hard device to make. But once we try to switch it to quantum, it becomes extremely hard. It's so hard that we don't, even nowadays, we don't have a very good theoretical proposal about how to do that. So for quantum hard drive, of course, the only difference is that instead of storing bits, we want to store quantum bits, the qubits. Okay, so instead of 0 and 1, we want to store alpha 0 plus beta 1. But other than that, the requirement is basically the same, that we want to we want to store it in the presence of finite error rate. And we don't want active error correction. We want to be able to unplug the device, put it in the drawer, and then after a long time, come back and retrieve it. And the part about passive protection is what makes hard drive hard, because you might ask, we already have a proposal for a quantum computer. How hard can a hard drive be? Well, for a quantum computer, the current proposal involves the element of active error correction. So people imagine that we encode information, we do the computation, and we look for error in real time and we correct it. And that's how we can have fault-tolerant quantum computation going on forever. Without active error correction, things become very hard. And that's what we want for the hard drive, because otherwise it becomes a computer. We can't carry it around in a suitcase. And it makes things so hard that we don't even know how to do it yet. But let me tell you people's effort in trying to solve this problem and what we found in the process. So in order to explain a little bit more about why quantum hard drive is so hard, let me spend a little bit more time on why classical hard drive can work. Well, classical hard drive can work because it's 2D magnet and we store information in the up and down domain. And if error happens where one of the little magnets get flipped into the opposite direction, well, it costs energy. So it's not that easy to happen. But what's more is that as the error domain becomes bigger, as more and more little magnets get flipped, as the errors accumulate, it costs even more energy. So the lower one has 4 qubits flipped and it costs energy in the units of 8, while the upper one, and this one costs only energy in units of 4. And this may sound stupid, but we never make a hard drive using 1D magnetic strip. And there's a very good reason for that, because 1D magnets are just not good enough. If we encode information in this one-dimensional domain, it can be very big. But if errors happen, the energy cost will be 2. And even if the error region expand, the energy cost remains 2 throughout the process. And eventually, everything is flipped and a 0 turns into 1. So if we plot out the energy, it goes from 0 to 2 and then back to 0. So there's so once the domain war between the red and black, once they're created, they're free to do random walk without requiring further energy input. And that's saying that it only takes polynomial time for a domain to be completely flipped, and that's not good. On the other hand, if we have a 2-dimensional magnets, then the energy cost actually becomes bigger and bigger and bigger as the error domain grows, and there's actually a linear energy barrier in going from 0 to 1, and that's what makes the 2-dimensional magnets a much better candidates for making the hard drive. So this extensive energy barrier turns out to be the key for making a classical hard drive. And because of this linear energy barrier, it turns out that information can be stored for exponentially long time. And that's a very good scaling, because you can just make the disks a little bit larger and make the domains a little bit larger, and then the storage time can increase by a lot. For a quantum hard drive, it's the story of storing the qubit. And we mentioned before that in order to store the qubit, we need to fight not one type of error, but 2 types of error, the bit flip error and the phase flip error, and that's all. Okay. And we can see immediately that the Turing code that I mentioned previously is just not good enough, because in Turing code, defects are made by drawing these red lines. And when I draw these red lines, defects only happen at the endpoint, because along the length of the red line, I don't see anything wrong. There's always loops fluctuating around, so locally I don't see anything wrong. But once I see the end of the string, the end of the red line, I see a defect. So this is similar actually to a one-dimensional magnet for a classical hard drive, where defects are made in pairs. And once they're made in pairs, they can move around and do random walk. So Turing code is actually not good enough for a classical hard drive. And we need to come up with something better. We need to come up with something that actually mimic the 2D magnet version of the classical hard drive. While this toric code, even though it's a two-dimensional quantum code, it only mimics the one-dimensional version of the magnet. So the most naive way to do this is actually to go to 4 spatial dimension because, well, we need 2 dimension for the bit flip error and 2 dimensional for the phase flip error, and 2 plus 2 equals 4. So there's actually, people actually knew back in 2001 that this is doable, that if we do live in 4 spatial dimension, we can find the error correction code that gives us exponentially long storage time as a quantum hard drive. But of course, unfortunately, we live in 3 dimensions. So the big question is, can we do this in 3 dimensions or lower? And amazingly, 10 years later, there was a graduate student at Caltech who proposed a model, and that's the model that in a way, maybe not completely started, but reignited the discussion, and which turns out to be the topic of Fractal today. So let me tell you a little bit more about the model. The model is it's rather complicated. So instead of going into the details of how the model works, let me just briefly tell you some of the key features. So this is a model on a 3-dimensional regular lattice. You see this is cubic lattice with degrees of freedom on the dots. And it looks regular, but there's actually hidden fractal structure in the model. And that's something that Joanne discovered. And at first people had a hard time to be convinced, but that's the amazing thing about the model. So let me start with some 2-dimensional picture of a fractal, and one of the most famous fractal structure in 2 dimensions is called the Sierpinski triangle. And here's how the Sierpinski triangle is made. Okay, so you start from one triangle. Yes.
So the slides are not switching.
Okay.
Maybe it's just slow. Yeah.
Yeah.
I can see
the fractal code. Okay. Okay. So right. So the Sierpinski triangle is made like this. So we start from one triangle, and then we take 3 triangles, and when we put the 3 triangles, when we take the 3 triangles together, they make a bigger triangle. And then we can take the bigger triangle, take 3 copies of that, and make an even bigger triangle, and then we can keep doing that. And that becomes a fractal structure, and that's called the Sierpinski triangle. So this is a 2D picture, but then there's a very similar one in 3D, and I try to draw it. And so you can start from the tetrahedron of the triangle. In 3D is a tetrahedron. You can start one tetrahedron and then put 4 tetrahedrons together to become a bigger tetrahedron, and then take the bigger tetrahedron and put 4 copies together to become an even bigger tetrahedron, and then just keep going like that. And that's the 3D fractal structure. And that's the kind of fractal structure that's hidden in Joanne's code. So this code is it's not on a fractal lattice. It's on a 3-dimensional regular cubic lattice with complete translation symmetry. But yet, the defects in the model, the errors in the model, moves according to this fractal structure, and that's what's amazing about it. Of course, that's because the code, the interaction that defines the code, is designed in a very particular way. And as a code, we know that Joanne showed that its defects, its errors, has to move through this fractal structure, and that's something that people never knew before that could happen in a condensed matter system. In condensed matter system, we can have a defect, and then the defect usually has some momentum, and then has some energy, and then, for example, you can have an electron, and then in the conduction band, and then the electron would move. Or you can have a quasi-particle, like in the toric in the topological model that I mentioned, and then they can move. But then in Zhou-Wen's model, the defects have to move through this fractal structure, and that restricts their motion. And it turns out that this model, because of this restriction on the kind of motion of the defects, it behaves completely differently than all the three-dimensional models that we knew before. For example, it will have a logarithmic energy barrier, while all the previous ones we know have at most a constant energy barrier if you consider it as a quantum error correction code. So logarithmic is not finite, but it's not very fast growing either. But of course, conceptually, it's a big improvement. And then what happens is that isolated defects, isolated errors, do not move at all, and they get stuck. And the only movement comes when defects move in coordination with each other, because they have to move through this fractal structure. So for example, if you start from a single tetrahedron, there are 4 defects. And then if you want to remain 4 defects, then they have to increase their distance by 2, and increase their distance by 4. So they have to move in coordination. And that slows down all the dynamical processes in the system, and that leads to slow thermalization. It leads to unusual entanglement structure. And then what's also amazing about this code is that the code space, the ground space basically of the model, depends sensitively on the lattice geometry. And these features, they have never been seen before in all the other models that we know in 3 dimension or any other dimension. And because of this very weird fractal structure hidden inside the model, there's no obvious continuous limit. And that's also a big trouble, because the folklore in condensed matter is that the model may be ugly, and the details might be too hard to find, but if you zoom out and if you forget about all the details, you can find a very nice continuum description of the low energy physics. And that has always worked so well for condensed matter, but this model turns out to be a big challenge to that idea. And that's how it becomes a topic for field theory as well. And I'll come back to that. So that poses the question of what kind of order, what kind of phase is this? And this is, of course, not a error correction question. It's a condensed matter question. And people in condensed matter just look at this example and say, how does it fit into everything we understand about quantum many-body systems? And when we say we want to understand something in condensed matter, we say, what is the order and what is the phase? And of course, then there's the related question of whether there could be a fractal field theory describing it. So this is again an even more amazing case of how quantum error correction codes inspired study of a whole new topic in quantum condensed matter. And I want to tell you a little bit, even though I'm running out of time, but I want to tell you a little bit of what we did in terms of the first question of the notion of phase and order. And I'll leave the second question because you have a local expert. Yongbak has worked on field theory along with other people in the field. So I won't say much about that, but hopefully I can explain a little bit about what we try to do in order to define phase and order for these fractal models. So it turns out Zhou-Wen's model is too hard. I don't have a good idea about that, but there have been other models, and even back to 2005, people have been proposing models that falls into what we call fractal model class. nowadays, of course, in 2005, it was not called Fractal. The name Fractal maybe was coined in 2015 or something. But these models have been known. And these models, which doesn't have a fractal structure, but share many other similar properties as the fractal one. For example, that the errors and defects are isolated, and when they're isolated, they don't move, and that leads to slow thermalization, unusual entanglement, and the sensitive dependence on lattice geometry, and the lack of obvious continuous limit. And these are all shared between the so-called foliated fractal model with the fractal one that I was telling you about. And this foliated one is something I could say something about. I could put my hands on and try to come up with a notion of phase and order for this subclass of fractal model. So this word foliation refers to the layer structure within a high-dimensional space. For example, for this rock, there's some layer sediment. So this is a three-dimensional version of a foliation, and that's exactly the kind of structure that we make use of, the subdimensional lattice structure that we make use of when we try to define the notion of order and phase. So let me back off a little bit and talk about the notion of phase, because phase is arguably the most fundamental idea in condensed matter. This is a phase diagram of water. We see there's solid, there's liquid, and there's vapor. And we know that liquid and vapor are basically the same thing, and they can tunnel into each other through the critical point. But solid is a different species, right? Solid is different from liquid and vapor because solid has a crystal structure. The ice has a crystal structure, while liquid and vapor don't have a crystal structure. So the important difference between the solid versus the liquid and vapor phase is the existence of crystal structure, or in other words, breaking of translation, full translation symmetry in water. Well, on the other hand, there are unimportant properties like the exact pressure, the exact density, and exact temperature within this diagram. If you just change the pressure, density, or temperature without changing the crystal structure, then we would say that the system is roughly the same, they stay in the same phase. And that's basically the idea of universality. So for water, we have a very good understanding about what are the important properties and what are the unimportant properties that allows us to group different water into phases, different water samples, basically, into phases. And this similar idea works for topological phases. Here I'm just showing you some diagram. This is an image made by Greg Moore. And we also have very good understanding about what's important and what's not important about topological phases, such that we can put them into phase diagram. For fractal phases, things are different because, well, the whole field started from a handful of examples, exactly solvable examples. And at the beginning, there's no obvious relation among them. So they're just very scattered and each one looks different. And it's hard to say how they are related to each other. And if you look at some of these models, for example, here I'm actually showing you the fractal model Hamiltonian. I don't want to explain that. And this is one of the foliated one. And what I illustrating here is the formula for logarithmic ground state degeneracy. And you can see how complicated they are, how different they look. And especially the fractal one looks totally ugly. And then the question is, when we try to decide which phase they belong to, which number should I look at? I can't tell here. I basically can't tell which number I should look at within this formula in order to tell which phase this model belongs to. And here, for the foliated one, things are better, but this is a function that depends on system size. And then it's still tricky because do you look at the first number or do you look at the second number, or but that's hard to tell because it depends on the measure of length, the measure of distance. And without translation symmetry, we lose track of everything. So it becomes a big problem of deciding how we want to define universality and how we want to tell what properties are important and what properties are not. And our idea is that this is because there's some mess hidden in the system, and that's making the whole thing more complicated than necessary. And what's hidden in the system are some two-dimensional foliation layers. And for this particular model, it turns out the so-called XQ model, it turns out that there's some two-dimensional toric code, the toric code I was telling you about, hidden inside. And not just one, there's actually many, many, many layers hidden inside. And that make the system look super complicated, but also because of a not very interesting reason, because if we know, we understand well topological order in 2D, like toric code. If we just stack them up into a three-dimensional model, it is different. It is non-trivial, but it is non-trivial for a very trivial reason, because you stack up something that you already understood. So what we realize is that these kind of stack is something that we want to ignore, is something that we want to define as the unimportant part of the system, while anything that cannot be assigned to be due to the stack of two-dimensional things are the core. They are the important part of the system. So that led us to define what is a foliated fractal phase. We basically say that anything that differs by these kind of stacks, that's not important difference, and we want to consider them to be equivalent to each other. So when we compare different models, fractal models, we want to model out the contribution coming from two-dimensional layers. For example, the excitations, the entanglement, anything that can be attributed to the stack of two-dimensional layers, we'll say they're not important. And that led us to some progress with trying to put a phase diagram onto these set of scattered dots of models. Of course, Haar's code is not within the foliated structure at all. It's fractal. We don't know how to deal with it. But for many other models, well, some of them proposed by Youngback and Kevin, we were able to establish relation between them using this understanding of what is important and what is not important. Okay. I don't have time to go into details, but I just want to leave you with the idea that if we mod out substructure from some lower dimensional submanifold, that allows us to understand what's important, what's intrinsically 3D for these fractal models. So let me try to put things together and try to summarize. We talk about magnets as classical hard drive. We talk about topological order for quantum computation. And then we talk about the fractal order, which, well, was supposed to provide a possible route for quantum hard drive, although it doesn't completely go there yet. We still need to make more effort. And then we see that as error correction codes, they perform very different roles. And then physically, and that's because they have very different physical structure. First of all, the kind of regular order does not depend much on spatial structure at all. Whether you have a magnet of a different shape, it doesn't really matter, right? But if you have a topological order, it sensitively depends on the topology of the surface. If you have surface with more holes, you will be able to encode more qubits. And then finally, for the kind of fractal order, it depends sensitively on the subdimensional geometrical structure, either the fractal structure or the foliation structure. At least that's how much we understand about fractal so far. And then for the first kind of order, the phase and phase transitions are all very well understood. It's the Landau paradigm of symmetry breaking, and there's a very nice field theory description of the phase and phase transition. You have an order parameter, and the order parameter goes to criticality. And then for the topological one, it's also theoretically pretty well established. Experimentally, there has been quite some success, although it's still under exploration, and people are trying very hard to realize them. And then the field theory description, well, it requires some newer ideas, but it's also pretty well understood for the most part. So it's not a huge challenge compared to the fractal one, because, well, first of all, for the phase and phase transition part, we're just starting to understand something. And for the foliation one, we had some success, but, well, we already know that it's way far away from the full picture. And of course, experimentally, there's experimentally, the effort is just beginning. People are trying to maybe do something, hopefully. And then the field theory description is an unknown, because, well, it's not completely unknown. There has been work by Youngbeck and others proposing how to use field theory to describe it, but it's far away from a complete framework. It's definitely beyond the conventional field theory. And well, I think the key is to add the subdimensional geometrical features into a field theory that breaks down the continuum picture people always have for field theory, but how much we can tolerate that, how much we cannot, and that is a total open question. Okay. So that's where I want to end the talk. I'll just say that this is an exciting area of what I want to call quantum many-body physics, where quantum information, condensed matter, and field theory come together and inspire each other. And I want to thank I want to thank all my collaborators and students and postdocs that were actually the main drive behind the project. And thank you for listening.